Here we're doing just a basic intro to variation of parameters method. We see this very commonly when we go to second order equations that are non-homogeneous. Before we start the video and go any further, I would like to point out a couple things. You want to make sure that you're okay with working with the auxiliary equation before we go on. So if you're unfamiliar with how to write the polynomial that either you called auxiliary or characteristic, or that equation, you want to make sure you're okay with that and have seen some of that before. So if not, check out our videos on the auxiliary equation and how to solve the homogeneous equations of second order type. And then the second thing you want to make sure that you've seen is the idea of the Wronskian at some point in time, or at least be familiar with determinants before you go through this video. So in this video we're working with the second order equations. So our highest power of, or the highest order of derivative is second order. We've got our linear left-hand side here, and then for it to be a non-homogeneous equation, we have some function over here, and we're going to be specific and say, well, g of x is not going to be equal to 0 in this instance. When it was equal to 0, we called that homogeneous of second order. Then our solution form is basically going to be y equals y sub c plus y sub p. Let's look at what we mean by that. So y sub c is what we call our complementary function. The complementary function, that's the part that we get when we solve the associated homogeneous equation using the auxiliary equation. And we'll do an example so you can tell what we're talking about if you're unsure in just a minute. Y sub p, we're going to look at a procedure using what's called the Wronskian, basically looking at determinant of a matrix involving our function and its derivatives, some of its derivatives. It's going to be based on the form of the y sub c, and it's also going to have to do a little bit with that g of x as well, and you'll kind of see what's going on with that. So there will be two parts. We'll have to find y sub c, y sub p, and then when we write our solution y, we just want to make sure that all of the pieces we found generally are linearly independent when we go to write our solution down. Here we've got an example, y double prime minus y prime minus 2y equals 4x squared. So we will look at finding y sub c, the complementary function, and we will look at the left-hand side and write down the auxiliary equation, which would be m squared minus m minus 2, and we look at solving the homogeneous form there. So we think about it being equal to 0. This will factor, giving us m minus 2 times m plus 1 equal to 0, giving us that m is equal to negative 1 and positive 2. And so that will give us that y sub c, the complementary function, is some constant times e to the minus 1x plus some constant times e to the 2x based on those values for m. So if you're at all lost at this point in time, make sure you go back and check out the video about auxiliary equation and homogeneous equations. Okay, moving forward. So we have our complementary function here. Now we need to find the particular function. Our particular solution here is going to fit the form u sub 1 times y sub 1 plus u sub 2 times y sub 2. We already have y sub 1 and y sub 2. Based on the form of our complementary function, we have a constant times a function plus a constant times another function here. So what we really already have is that y sub 1 is equal to e to the minus x, and we have that y sub 2 is equal to e to the 2x. So we already have those two pieces down. Where we get u sub 1 and u sub 2 from comes from the idea of the Wronskian, and so let's look at that. So we're going to have to find three things. We're going to have to find the Wronskian for these functions, and then we're also going to have to find what I'm going to call W1 and W2. They're Wronskians, but with certain columns inserted. This idea we're going to work on here is based on the idea of Cramer's rule. You may have, back in pre-calculus or something, solved systems of equations using determinants and Cramer's rule, so this is based on a very similar idea as Cramer's rule. So first let's at least find w, the Wronskian, based on these two functions here. So finding w, that would be the determinant of the matrix with these functions for its first row, e to the minus x, e to the 2x. Next row would be the first derivatives of those. So we'd have negative e to the minus x and 2e to the 2x. Take the determinant of that. That will give us e to the minus x times 2e to the 2x minus negative e to the minus x times e to the 2x. So if you're not familiar with Wronskian or determinants, now's the time to go check that out before you go any further. And then that will give us, let's see, 2e to the x plus, and then that will give us e to the x. So w, it looks like, is going to give us 3e to the x there for w. So we've got that answer there. Now we need to find w1 and w2. What we mean by w1 is we're actually going to take out the first row of our original Wronskian, or sorry, first column of our original Wronskian, and we're going to replace it with all zeros, except in the last spot we're going to place g of x, and we're going to start using this 4x squared here. Okay, so let's just do w1 and w2, and hopefully you'll kind of see the idea of what we're doing here. So w1 is going to be equal to the determinant. So w1, take out the first column, replace all zeros except for the last entry should be g of x, which is 4x squared. And don't touch any other columns, so we'll leave e to the 2x, we'll leave 2e to the 2x. So we find the determinant of that matrix, that'll be w1. w2 means we will swap out the second column of our original Wronskian. So in the second column we will have a 0 and 4x squared. And then in the first column we had e to the minus x and negative e to the minus x in the original. So now we'll find the determinants of those, and we'll have w1 and w2. So w1 will equal, so this diagonal is going to give us 0. So we'll have 0 minus 4x squared e to the 2x. In other words, just negative 4x squared e to the 2x. And then over here for w2, that's going to equal e to the negative x times 4x squared minus, and then when we do this diagonal we'll get 0. So that will just give us 4x squared, we'll call it e to the minus x. So now we have w, we have w1, and we have w2. So let's look at where u1 and u2 start to get developed. Alright, so developing u sub 1 and u sub 2, so we want to note that u sub 1 prime, the derivative of u sub 1, is going to be w1 over w, and then u sub 2 prime, the derivative of u sub 2, is going to be w2 over w. Okay, so w1 over w would be negative 4x squared e to the 2x over 3e to the x. w2 over w would be 4x squared e to the minus x over 3e to the x. So that would give us that u sub 1 prime is negative 4/3 x squared e to the x, and u sub 2 prime is equal to positive 4/3 x squared e to the minus 2x. Alright, so in order to arrive at the original u sub 1, u sub 2 that we'll plug in and get our final y sub p, we need to then integrate with respect to x. So, in other words, u sub 1 is going to equal, I'll go ahead and bump the negative 4/3 out since it's a constant, so that would be negative 4/3 integral x squared e to the x dx, whereas u2 is going to be, I'll bump the 4/3 out again, the constant, integral x squared e to the minus 2x dx. You would integrate both of these by parts. I'm going to go ahead and skip the commercial on the integration by parts and just cut straight to the solution there. We're assuming you're okay with integration by parts here. If not, check out some integration by parts videos we have. So that would be negative 4/3 x squared e to the x plus, let's see, 8/3 x e to the x minus 8/3 e to the x. technically plus c. We won't be using the plus c part though. And then u2, that would give us, let's see, negative 2/3 x squared again, e to the minus 2x this time, minus 2/3 x e to the negative 2x minus 1/3 e to the minus 2x. So I skipped the integration step here, so don't think it's magic. We're just not showing it for the sake of shortening the video. It would be pretty lengthy. Okay, so we have u1, we have u2. We want to put those here and here. Remember, we already said that y sub 1 was going to be e to the minus x, and we already said y sub 2 was going to be e to the 2x. So we'll be putting in all our information, and we'll get y sub p there. All right, so then y sub p is going to equal u1 y1, so we'll take all of this expression and then we'll multiply it by e to the minus x, and you can see that would take care of eliminating all of the e to the x terms. So our u1 times y1 then will just end up being negative 4/3 x squared plus 8/3 x minus 8/3. And then plus our u2 times y2. So here, what we would end up doing, multiplying in y2, which was e to the 2x, into that, eliminating all of the e to the minus 2x terms. So that would then give us negative 2/3 x squared minus 2/3 x minus 1/3 when we did u2 times y2. And then you'll notice we have some like terms in all of these. And so it turns out when we combine this and this, we get negative 2x squared. When we combine the 8/3 x and the minus 2/3 x, that'll give us a plus 2x, and then the minus 8/3 and minus 1/3 would give us minus 3. So that's our y sub p. We just need to combine that with our y sub c, which we already have, and then we'll have our answer. So our answer to our second order equation here is going to be c1 e to the minus x plus c2 e to the 2x minus 2x squared plus 2x minus 3. So variation of parameters is a more lengthy procedure. If you can use the undetermined coefficients method, or even if it's just homogeneous where it's equal to 0, those are generally shorter methods, but variation of parameters will handle more cases than those. So it's a more useful method, but it does take a fair amount of time. Okay, just to sum up the method, so first we start by looking at our linear second order equation equal to some function. We solve the associated homogeneous form using the auxiliary equation, using our polynomial in terms of m and maybe factoring or solving. That gives us the complementary function. Then once we have y sub c, that should give us the form including y1 and y2. We'll then use those y1 and y2 functions to develop our Wronskians. So we'll need to develop the original Wronskian, we'll need to develop w1 and w2. Once we do that, we start using those to establish what u1 and u2 are, and then we go back and multiply u1 times y1, u2 times y2, we add them up, that'll give us the particular function, which we then include with the complementary function as the solution.